So in the previous lecture, we have looked at the meaning of divergence, and we have seen that divergence of a field here refers to the rate of loss of a particle, whether it be heat or water, from a certain volume. And we have also mentioned that the divergence can be non-zero in certain cases, right? So here we are going to look at what are these two cases where your divergence of the field is not equals to zero. So if you look back at the equation that we derived previously, we have this divergence of a field, which is given in here. Let's just point this. So in this case, my field is my V, and divergence of V is written like this, and we have said that this is the rate of loss per unit volume. So now let's consider a flow of liquid, for example, in a given tube again. And now we have the water flowing from the left to the right, and this will give you the divergence of the field. And if let's say there is another flow of liquid which goes from the right to the left, and if these two rate of flow is the same, then you will have the divergence to be equals to zero. So it means as we go, let's say we start with a time t equals to 0, and we end up with a time t, the rate that goes from the left to the right and the right to the left are the same, and therefore you have divergence to be equals to 0. But if you, on the other hand, if you have only a flow from the left to the right, then of course your divergence is not 0. Right. So the first case is that you have a change over a period of time, so that is the variation in time. It is 0 if the left and the right goes in the same rate. Of course, there is also a case where the divergence is equals to 0 if there is no flow at all. So, but we are not interested in this. And then the next case will be in the case where there is a source or a sink. But to give an idea of what a source and a sink is, I show you here a plot which I have made earlier, and this is basically a scalar potential. But what I just want to show you here is there is a minimum over here, and there is a maximum over here with a positive x. Positive x, there is a maximum, and negative x, there is a minimum. So here, if you plot the vector field, you have something like this. But if you actually plot the vector field, you take the gradient of the scalar potential, you will see that the vector field goes from the minimum to the right, because the gradient goes from a positive, from a lower negative towards a positive region. Right? But then if you take the negative of the gradient, then you have the vector field pointing downwards. So this is the plot where you have the negative of the gradient. Now, what is the relation to source and sink? Here, I just want to take the analogy where the positive here, this is the source, and the negative here is the sink. So if you just imagine you are standing at the top of this slope over here, you will have a tendency to go downwards, right? So basically, that is the same analogy for example, heat. So if you hear this is hotter, then you will have a tendency to go for the heat to move from here to here. So you can either have a source, which is this one only, a place where there is more or extreme heat, or you can have a place where you only have the sink. So this is the sink, where let's say for example this is the place which is more colder than the rest of the place, and then you have heats from everywhere going towards this place. So the next so here basically I want to show you here is that the divergence of the field is non-zero if you have a source or a sink, or both of them together. So now we are going to look at the equation of continuity. Right, so now we know the divergence can be equal to 0 or non-zero. So now we need to take into account the case where the divergence is non-zero. So in order to write the equation, we have an expression like this. So this is the divergence of the field, and we have this term, which is a partial derivative of rho with respect to time, and rho can be anything, for example charge density. And then you have a term which is psi here. So in the next few minutes, I'm just trying to explain what is the logic interpretation of this equation. So again, I'm going to use the plot that I've shown in the previous slide, and here we take this to be the source. This is the place where you are at the top of the slope, and this is the minimum, and we shall take this as a sink. So this psi in this equation refers to the density, the difference in the density of the source and the sink. So basically, if the source has a larger density with respect to the sink, then you have the flow from the source to the sink to reach equilibrium, right? So if the source and the sink has the same density, then of course there is no flow anymore, because they are already at equilibrium. And the one way to picture this is to consider the case of heat, where the heat goes from a higher temperature to a lower temperature. And the other case is where you have a flow of particles from one side to another. So the partial derivative of rho with respect to time basically tells you how much particles comes into the system. So this is the rate of increase over time. And of course, the other one is divergence of the field. This is how much goes out. So this is kind of an analogy to explain what is this equation all about. So you have a density of the source and the sink. So the source and the sink will cause you to have a flow of particles, any physical quantities, and you have the rate of increase, and then you have how much that goes up. So let's take an example of the case where you do not have any sink or a source. So you have no sink, no source, and therefore you will have del of the field vector plus the partial derivative of rho over time to be equals to 0, because my psi is equals to 0. And this is a general expression, which is the continuity equation that you have seen in a lot of physics applications, right? So this is valid for a case where the quantity is conserved, for example energy or number of particles in the system and so on. So now let's consider a particle in a box here, right? And if let's say the particles goes out, it moves out over time. So basically in this case, the gradient of the vector of the field vector is going to be positive because it's outgoing. And I just have to rearrange this equation over here so that I have a partial derivative of rho with respect to time, and this is equals to negative of the gradient of the field. And since the gradient of the field is positive, right, as we have mentioned, because it's outgoing, and then this you have the rate of change of this rho, which is the density, for example charge density or density of the water, and this is going to be negative. So it means the rate of the change of the density over time is going to decrease, right? So basically this is the idea of the continuity equation. So you have the continuity equation when you do not have any sink or source. So this continuity equation is basically a more specific case, whereas this expression over here with the sink and the source is a more general equation as compared to the continuity equation over here. So now there is another case where your divergence of the field is non-zero. That is when your partial derivative of the density over time is equals to zero. Basically this term is equals to zero, but then you have a source or a sink or both. So in this case, your gradient of the field is going to be equals to the difference in the density of the source and the sink. And you have this case in electromagnetism. So if you look at the divergence of the field, you will see that the divergence of the electric field E is equals to the charge density over the dielectric constant. So you have already seen this equation, but most importantly or more interestingly, you have cases where you have the divergence of a magnetic field to be equals to zero. So we will talk about this in the next slide. But let's look at the divergence of the electric field here. So if you look at the electric field, this is the field that is produced by the charged particle itself, right? So for a negative particle, right, they are going to have a divergence of the field inwards. So this is a negative uh, divergence, right? So the field is going inwards. Whereas for a positive particles, you are going to have the divergence of the field going outwards. So you have something like this, right? So now let's go to the divergence of the magnetic field. So I mentioned just now the divergence of a magnetic field is equals to zero. But why is this so? So in the case of magnetic field, you do not have a charged particles that is free going to become the pole. So you do not have, for example, a positive charged particle exiting magnetic field, right? So you do not have a specific pole like this. So because you do not have a specific pole like this, therefore your source is equals to zero, right? So in this, but instead of a free pole, magnetic pole, you have a system which consists of a positive and negative uh, bar, right, like this, and the gradient of the field for this whole system is going to be zero, because over here you have outgoing, which is divergent positive, and then you have at the south pole over here you have a negative gradient. So in total, this whole system, you have divergence of the field to be equals to zero, because outgoing, incoming is the same. So this idea of divergence of this magnetic field equals to zero tells you that there is no magnetic monopole. So if there is a magnetic monopole, then the divergence of the magnetic field is not going to be equals to zero. Right, so this is an example where you apply the divergence of a field in specifically electromagnetism. So I want to try to summarize what we have discussed in the case where the divergence of the vector field is non-zero. So there are two situations which you can simplify this expression. So when your divergence of the field is non-zero, you have two terms over here. This is the partial derivative of the charge or whatever density, and then here you have a psi, which is the difference in the density between the source and the sink. So of course now you have three situations actually. You have a general expression like this, where you have the change in the density over time and you have a source, or in the case where you have no source but then you have a change in the density, or you have no change in density but then you have source. So now let's look at the first case, right? So the first case, you have no source or sink. So basically, you have psi equals to zero, and then you have this expression which looks like your, which is not, which is exactly right, exactly your continuity equation. And the best example to think of this is to look in terms of a flow of water, liquid, or maybe blood in a tube or vessel. So here, this clearly shows that you have a change in the density over time, because over here, as time progresses, your density is changing, but then you have no source, so you do not have an additional supply of water or blood into the system, right? So if you are talking about, let's say for example, blood transfusion, so you have a addition of a blood coming from external source into the system, and so this is your source. But then for this continuity equation, there is no such thing, and you do not have a source, and this is your representation of this equation that you can think of. Okay, I'm just trying to give you an idea of how to picture this equation. So there is a divergence, there is a gradient of the vector field which is non-zero, and this is related to the negative of the partial derivative of your water, for example, density with respect to time. And then there is another case where you have change, where you do not have a change in density, because now partial derivative of rho with respect to time is 0, but then you have a source, right? So what does it mean that there is no change in density? So here d rho over dt is equal to 0. So basically the number of density in the system is conserved. So there is no change in density, which is the opposite of this case, because if you look at this, there is a flow of water or liquid from left to the right, and then you have a change in the density. So here we have applied this expression on the right hand side here to the case of an electromagnetic field. So for example, in the electric field, you have a source. What is your source? Your source is your negative charge particle or your positive charge particle. So your positive charge particles exert a gradient of the field outwards. So you have a picture like this. Whereas for the negative charge particle, the gradient is going inwards. So you have a vector field that looks like this. But then what about magnetic field? So when you talk about magnetic field, you do not have a source like this. You do not have a particle that acts as a source that emits a magnetic field, because magnetic field comes about due to the movement of the charge. So therefore, the gradient of the magnetic field is equals to 0, because you do not have a monopole. So if you have a monopole, then you have this picture. You see, you have a charged particles or something like that that emits a magnetic field, but you don't. When you don't, you have the gradient of the magnetic field to be equal to 0. So what you have instead is a magnetic dipole. So this is a magnetic dipole. You have a positive pole and you have a negative pole, and then the magnetic field is moving in a closed circuit like this, and therefore the gradient of the magnetic field is therefore 0.